So 28 here.
Revision book.
Yes, revision book. Did you have it on your laptop?
Page 16.
If you were given a light spiral spring of length 12 centimeters and mass 200 grams attached to one end, explain clearly how by holding the spring vertical at the top end you will be able to demonstrate the effect known as resonance in a mechanical system. Okay, so what we got here is you've got a spring and you hold it here and the length is 12 centimeters and this here is 200 grams. So 0.200 G actually, if you want, like this. So that's about 2 newtons. Who remembers this word? Anybody? Resonance? Anybody who remembers what is it? No? Yes, go ahead.
It's when something increases with body. The oscillation
Thank
gets stronger.
Close. So resonance is this. When you apply a force here that is frequency F, and if that is the same frequency here, what will happen is this will get much bigger amplitude. Okay, so for example, if your spring is going, let's say 1 per second, so it's going 1, 1, 1, 1 like this, okay? And then if you hold the top of it and then you do the same thing, move it up and down, then the result is it'll still go 1, 1, 1 here, but it'll go twice as far. And if you remember, this is true even if this here and this here are being done at different times, you know? Because I remember people saying, well, what happens if this goes down when this one's going up? Remember we were talking about this? In fact, it doesn't matter. So this is called resonance. Resonance is when, I suppose you could say, the outside force is applied at the same natural frequency.
So it's 200 gram or no?
Sorry, when I write it like this, I meant 0.200 G. It was 200 grams. Look it, I have it look like it's coming from the clock. So if I move this up and down, at the same frequency this is moving up and down, the result is the amplitude will get bigger. So sorry, I'm not finished my sentence. The outside force is applied at the same natural frequency causing an increase in amplitude. Now, let me open up the formula book actually before going on. Next example.
So it's the last one. So
Yeah, I said the outside force is applied at the same natural frequency, causing an increase in amplitude. Okay. Now, I just need the formula book to show you something for the next one. So look, we have the formula here for a mass on a spring. That's what we have here. That's it right there. Okay? T equals 2 pi root m over k. So if I look at the next part now, T equals 2 pi root k over m. And he wants the k. And we know that the m is 200 grams. So we have T equals 2 pi root k over 0.2. He also tells us that the frequency is 1.25. Does anybody remember a formula that relates frequency and periodic time? 1.25. Yeah, 1 over f equals t. Is that in the formula book? It might be in there somewhere, I don't know. Anyways, 1 over f equals t. So here, t would equal 1 over 1.25, which would be 1 over, so that'd be 0.8. Right? Seconds. So I can go back here and say 0.8 equals 2 pi root k over 0.2, and I can get the k now. Got a really small number, k equals 3.2 times 10 to the minus 3. That's my answer for k. Okay, got that? Now, if you look here, what else have we got it for? Yeah, it's not actually there in the book. The only formula you have for a mass on a spring is its time here. But what type of motion is that when it's going up and down like this? What's the name of this motion? Yeah, simple harmonic motion, okay? So, simple harmonic motion. That's when it's going up and down. Yeah.
So that's clear. Yeah.
Huh? What's wrong? You need me to move it? What are you saying it's not clear?
Yeah, because you can't recognize the words.
Oh, this is SHM. Simple harmonic motion. Now, if you remember, there's a formula that tells you how much energy is stored in the spring. Just give me a second, I'll try and remember it. It is a half k delta x squared. That's how much energy is stored in the spring. Where delta x is the, yeah, it's the extension. We know the K, I just got it previously, 3.2 times 10 to the minus 3. And he says that it's stretched to twice its original length. So its original length is 12 centimeters. I can't remember if it's delta x or if it's x, if it's the extension or if it's the length. I'll check the answer in the book now, but I think if it's twice, then I should put in here. Oh, now this is my question. I don't know if I should put in 12 or if I should put in 24. So I don't remember this formula exactly. You don't have your notes.
To see the answer.
No, you don't have the. No, I'll get the answer here. No, I'll get the answer here. Just be cool.
Biology.
Let me just find it first. Spring. No spring in that exam. No spring in that exam. None in that one either. It must be down in here.
Is x squared
It's x squared, not.
half k x squared?
It might be in one of these. Yeah, I thought it might be that. Oh wait, I got. Wait, actually, you know what? I have the notes right here. Let me just check. Where am I going? Here we are. Physics, part 1, mechanics. I just can't remember if it's x or delta x. Energy. It's the amplitude, meaning the maximum, how much you pull it. So I feel like if you have a spring of 12 centimeters and it's at rest, and then you pull it another 12, then that extra 12 is the amplitude. It's how much you pulled it from the rest position. So that answers my question. I should be using here 12, and it should be delta x, or maybe actually to make it a bit clearer, not delta x, but to write in amplitude, the A, how much you pull it out. I think would be best. This is not in the formula book, and it's easy, as you can see, to forget how to use it. So please make note of that. It's important. It should be, well, A will be better, big A.
Mr. A, I think, could mean 24, right?
Not really. This is the problem. The A doesn't mean the length of this. Yeah. So the A is the extension past its natural rest position, not the length of the spring.
If I write delta x, is it right or wrong?
The more I wouldn't take any marks away from you. What's more important is which number you put in. Anyways, to me it seems clear that I should put in 12. But I suppose that makes sense, because there shouldn't be any energy stored in it if I don't stretch it.
Yeah.
So no stretching means 0, but the spring is still 12 centimeters long. So let's see what we get.
Still squared.
And it's squared as well, isn't it? Yeah, it's squared as well.
So which means the 12 is the original length.
Yeah.
I thought it.
No, 12 is the original length, and they pull it 12.
Full again.
Pull again, yeah.
It's 0.2.
I got a tiny number here.
0.2.
Yeah, oh, it's tiny. It's 0.02 millijoules.
Sir, I got 0.23 only.
Let me double check. So 3.2 times 10 to the power minus 3 times 0.12 squared divided by 2. So I got 2.3 times 10 to the minus 5. Yeah? 2.3 if you want.
Zero point zero,
0.12. Did you put in 12? It's 12 centimeters.
It's probably you have to prove it.
I thought it was.
That'd be a good stretch on your spring, 12 meters, yeah. There'd be a lot of energy in that.
And the building must be really tall.
Yes. Okay, I'll stop this one here.